Okay, we are looking at starting chapter 9 on testing a claim, which is significance tests or hypothesis tests. Section 1 here is learning the basics of significance test. So we're going to be looking at stating null alternative hypotheses for a significant test about a population parameter, interpret p-value, determine whether the results of a study are statistically significant, and make an appropriate conclusion, interpreting type 1 and type 2 errors and giving consequences of each. So a little bit of an intro here. We talked about confidence intervals in chapter 8, and now we're in chapter 9. So confidence intervals are one of the two most common types of statistical inference. Confidence interval is when we want to estimate a population parameter. The second type that we're going to be starting to talk about here is the significance test, which is to assess evidence provided about a claim. So we're going to state whether or not we're going to find statistical evidence in one direction. So a significance test is a formal procedure for comparing observed data with a claim, which is also called a hypothesis, whose truth we want to assess. The claim is a statement about the parameter, like the population proportion p or population mean mu. We express results of a significance test in terms of probability, measuring how well the data and the claim agree. Okay, so this graph did not turn out well, but what we're looking at here is somebody who claims they're an 80% free throw shooter, but we think that he's exaggerating. So to test this, we're going to ask him to shoot free throws. This is a applet, so it's just a simulation of his shooting free throws. What we would expect is certainly it to bounce around a bit, but then even out towards 80 as we go further along in his attempts. If he takes 25 shots, record how many of the 25 he makes, do 25 again, repeat until you are either convinced that he makes less than 80% or if his claim is true. So to talk about how we're going to phrase that or how we're going to work through that problem, we have to talk about a few things with significance tests first. The claim that we're weighing evidence against is called the null hypothesis. That's the initial claim. And we call that HO, H sub O. The null hypothesis is a statement of no difference. That one's going to be equal to whatever the claim is. The claim about the population we're trying to find evidence for is the alternative hypothesis, which we're going to call H sub A. H sub 0 is the claim, and H sub A is what we are testing it against. So in the case of our free throw shooter, he's claiming to be an 80% free throw shooter. So the null hypothesis is P is equal to 0.8, and the alternative, we think that it's less than that. So the alternative is going to be less than 0.8. So the null hypothesis is always going to be in the form a parameter equals the value that's being claimed. The alternative hypothesis is going to be one of the three following. We're going to have the parameter is less than the value, which is the one that we just had, where we think that the claim is actually less than what they claimed. The parameter is greater than the value claimed, or the parameter is not equal to the value claimed. So it's going to be in one of those three forms for sure. The alternative is one-sided if it's one of the top two, where it states that it's either larger than the null or less than the null. And it would be two-sided then if it's that bottom claim, the not equal to. The hypotheses should express the hopes or suspicions that we have before we see the data. It would be pretty silly for us to make our claim after we analyze all the data, because that's basically mathematical cheating. The hypotheses always refer to a population, not a sample. That's why we use the word parameter in all three of those hypotheses earlier. It's always going to be in terms of the population parameters. It's never correct to write about a sample statistic, such as p hat or x bar. Okay, so let's look at a couple examples. In each of the following, let's describe the parameter of interest and state the appropriate hypotheses based on the scenario. According to the website sleepdeprivation.com, 85% of teens are getting less than 8 hours of sleep a night. Janine wonders whether this result holds in her large high school. She asks a simple random sample of 100 students at the school how much sleep they get on a typical night. 75 of the responders said less than 8 hours. So we need to first state what is our parameter, and that'd be P. We're talking about the proportion of students who get less than 8 hours of sleep. This is specifically at Jeannie's high school. And then our two parameters for this scenario. The HO, which is our initial claim, is that the proportion is 85%, 0.85, and our HA, which is the alternative, is claiming that here's where the statement is that we know the direction of our alternative. It says Janie wonders whether this result holds in her high school. So it's not saying which direction she thinks that it's going to go. She just wonders whether it's true. So that's the not equal to. As part of the 2010 census, the U.S. Census Bureau advertised 10 questions, 10 minutes, that's all it takes. On the census form itself, we read that the U.S. Census Bureau estimates for an average household the form will take about 10 minutes to complete, including the time for reviewing the instructions and answers. We suspect the actual time is longer. Okay, so first, what is our parameter that we're looking at? It'd be the mean amount of time, so that's mu. Okay, and then our two hypotheses. The claim is 10 minutes, and when we have means, we do have to put the label in our hypotheses. Proportions you do not have to label. We think that it's longer than 10, so greater than would be our alternative. Okay, so going back to our basketball shooter, to test his claim, so we said that we had him do 25 at a time. So here, let's say we did 50 free throws and he made 32. He got 64%. Can we conclude, what can we conclude about the claim based on the sample data? If we did simulating 400 times that he shot 50, so these are all simulations, this did not actually happen, that would be quite a lot of 50 shots. If he's actually an 80% free throw shooter, this is a simulation of a whole bunch of trials of 50. Down here, that 0.64 is where he ended up. There are not very many down there. Out of the 400, there are 3 that are down there. So 3 out of the 400 at 0.64 or less. And the 0.64 is what his shooting percentage was. So that is 0.0075 chance that if he's really an 80% free throw shooter, the chance of, whoops, 64 or less is 0.0075. That was out of our simulations, we saw that happened 3 out of 400 times, which is 0.0075. That is extremely unlikely. If he's actually a 80% free throw shooter, to do that poorly and one set of 50 is not likely. So what can we do with that information? The observed statistic is so unlikely if the actual parameter is 80% that we're pretty convinced that the player's claim is not true. We don't think that he's actually an 80% shooter because it's so unlikely that he would have gotten such a bad sample if he's actually an 80% shooter. So the two things that could happen here is that the player's claim is correct. He actually is an 80% shooter. And just by chance, he had a really bad day. That happens, right? There were 3 out of 400 possibilities there. So a very unlikely outcome occurred for this guy today. What we think is that actually the alternative hypothesis is correct, and that the population proportion is actually less than 80%. So the sample result is not that unlikely. So our basic idea here is that if an outcome rarely happens if the null hypothesis were true, then we think that it's not true. Okay. So now we have to look at this concept of p-values. The null hypothesis is going to state a claim. We're seeking evidence against that claim. The probability that measures the strength of the evidence is called the p-value. The probability that's computed assuming HO is true, that the statistic would take a value as extreme as or more extreme than the one that actually observed, is the p-value. So if we have really small p-values, then we have a lot of evidence against our HO claim because they're saying that the observed result is really unlikely if HO is true. But if we have large p-values, then we don't have convincing evidence against HO because they're saying that we could very well have a result when HO is true. Okay, so let's look at an example here. We have calcium is vital nutrient for healthy bones and teeth. The National Institutes of Health recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned teenagers aren't getting enough calcium. Is this true? They perform the test that mu is equal to 1,300 or less than 1,300 for the alternative, where the mean is the true mean daily calcium intake for the population of teenagers. They asked 20 teens to record their food and drink consumption for a day. The researchers then compute the calcium intake for each student. Data reveals that X bar is 1198 and S is 411. After checking that our conditions were met, researchers performed a significance test and got a p-value of 1404. Explain what it would mean for the null hypothesis to be true in this setting. If HO, so our claim is mu is 1300, this means the daily calcium intake is 1,300, meaning teenagers are getting enough calcium. So now we have to interpret the p-value. So remember, we always make this based on the assumption that HO is true. So we say, if the true mean intake is actually 1,300, the chance of getting a sample statistic as extreme or more extreme than the one we got is, in this case, 0.1404. So let's see how we can say this. Assuming the mean calcium intake is 1,300 milligrams, the probability or the chances of getting a sample mean less than or equal to ours, which was 1198, purely by chance, is the 1404. So 14% chance of getting results of less than or equal to 1198 if 1,300 is true. That's pretty big. I'd say a 14% chance is reasonable. So I don't have any evidence to claim against my HO. Okay, the final step in performing a significance test is then to draw a conclusion about the competing claims that we're testing. We make one of two decisions based on the strength of the evidence against the null. We're either going to reject the null or we're not going to reject null. Because we failed to reject, we don't say accept, okay? That's not, we don't ever use that term, and we're never saying that we're accepting HO. We're just talking about either we reject or don't reject that null hypothesis. So in a nutshell, if we have a small p-value, we reject the null, and we have convincing evidence for HA. Just because we have convincing evidence doesn't mean we say that HA is true. We just say we have evidence for HA. If we have a large p-value, we fail to reject HO. And we do not have convincing evidence for HA. So our conclusions are pretty much written the same way, except with like the words fail to or do not in front of them. Otherwise, it's exactly the same. Okay. But how small is too small? How big is big enough to, how do we know what that number is when we're going to reject or fail to reject HO? And that is going to be based on a significance level. That's going to be based on the Greek letter alpha, which you will see me writing as that. Doesn't look quite as nice as the typed one, but that is the value that we're going to be comparing the p-value to know whether the p-value is small enough. So if the p-value is smaller than alpha, then we're going to say that the data are statistically significant. At level alpha. So it could be not statistically significant at a different level, which is why we have to specify at that level alpha. If it is statistically significant, then we reject the null and conclude that we have evidence to favor the alternative. So similarly to our last chart here, this time not just saying the p-value is small, but we're saying if the p-value is less than alpha, then we reject the Ho and have convincing evidence for HA. But if the p-value is greater than or equal to alpha, then we fail to reject Ho and we do not have convincing evidence for HA. So now let's look at this in context to a few scenarios. A company has developed a new deluxe AAA battery that's supposed to last longer than its regular AAA battery. However, these new batteries are more expensive to produce, so the company really wants to make sure that they do last longer. Based on years of experience, the company knows that its regular AAA batteries last about 30 hours of continuous use on average. The company selects a simple random sample of 15 new batteries and uses them continuously until they are completely drained. The sample mean is 33.9. The significance test is equal to 30 and greater than 30 for our two hypotheses. Mu is the true mean lifetime of these new deluxe AAAs. The resulting p-value is 0.0729. At each of these levels, what conclusion would we make? So we compare the p-value, which is 0.0729, to our significance level alpha. On part A over here, our p-value is less than alpha. So we would reject the null, and we would say that we have evidence that the company's new AAAs are last longer. But if we switch that to a different level of significance, like 0.05, that 0.07 is now larger than 0.05. So we fail to reject the null. And we just stay the exact same thing as that green sentence there, but we say we do not have evidence that the new AAAs last longer. There's always the chance that we made a mistake. We draw a conclusion, we hope that we're correct, but we could be wrong. There are two types of mistakes that we can make. When we reject the null, but the null is actually true, this is called a type 1 error. Alternatively, if we fail to reject Ho, but the HA is actually true, that is called a type 2 error. So here's kind of the box of the scenarios that could occur here. If the top left box there, if we rejected Ho, but Ho is true, this is a type 1 error. Going over to the right, if we rejected Ho and we were supposed to reject Ho because the Ho is false, then that is the correct thing to do. Bottom left, if we failed to reject Ho and Ho is true, good job, we did it, correct. But if we failed to reject Ho and the Ho was false. We should have rejected it. That is a type 2 error. The probability of getting a type 1 error is the probability of rejecting Ho, which is the significance level. So alpha, which is our significance level, is a type 1 error. That's the probability we get it wrong, that we rejected when we shouldn't have. So we always need to consider the consequences of these different errors when we do these and when we choose a significance level, because there are times where we don't want to incorrectly reject. That would be bad. So in this case, a type 1 error when we're referring to those batteries is we say that the battery life is actually greater than 30. When it's actually 30 in reality. A type 2 error would be not finding the evidence batteries are greater than 30. Oops. When it really is. Which one is more serious? Do we want to say that it's greater than 30 when it's not? Or do we not want to say it's greater than 30 when it is greater than 30? The two different consequences for the type 1 error would be that the companies are going to go ahead and make this new AAA battery saying, yeah, this is so much better, and it's not. And the type 2 would be the company decides not to make the batteries because they found out that it's not greater than 30 when it actually is. So I would think that the type 1 is worse because you're going to be deceiving the customers. The customers are going to buy this new battery and it's not any better. So you're deceiving your customers. That's not good. And hey, we finished. That's our section 1 here on the basics of significance test. We've covered all of these things. And here is the homework that we should be covering to practice.